Hello, and welcome back to CS492G, Foundations and Future of Virtual Reality, Artificial Intelligence, and Massively Multi-User Online Role-Playing Games. So we're in part 2 about Foundations and Future of Artificial Intelligence. So far, we've covered several aspects of artificial intelligence that are not part of the regular mainstream curricula, such as philosophy and pedagogy. And today we're going to continue and talk about foundations. There's an elaborate theory, actually pretty old, from the 1980s about learnability and about complexity of machine learning. This theory is rarely known, unfortunately. So today and for the next two talks, we're going to recall and present to you that theory of machine learnability and complexity of machine learning. With three talks. First talk about VC dimension, Vapnik-Chervonenkis dimension, which has many applications beyond machine learning. Then we'll talk about this theory of machine learning based on the Vapnik-Chervonenkis dimension, and in particular the Schellach-Sauer lemma. And we'll continue with the third talk about computability and complexity of machine learning based on these two concepts. So these are three talks in a row that build on top of each other. They're heavily mathematical and theoretical computer science. So I'm particularly, I like this a lot. So I'm happy that we have found three volunteers also with some background in mathematics and computer science, willing to present these three talks. And the start makes Abbas today, talking about the VC, the Vapnik-Chervonenkis dimension. So let me now give the screen and the microphone to Abbas.
Can you hear me? Can you hear me? Okay, hello everyone. Today I'm going to talk about the Vapnik-Chervonenkis dimension, and it's the table of content. I will start with the introduction and I will give the preliminaries that we need to understand the VC dimension. And then I will move on to the shattering. Shattering is the main concept to understand what's VC dimension. Then we will go into the more details of the VC dimension itself. And at the end of the presentation, I will introduce the applications and the beyond what we can do with the VC dimension. After finishing this presentation, you guys will probably be able to understand the learning machine, the preliminaries, shattering, VC dimension, other applications of the VC dimension, and other measurement tools. I will talk a lot about those measurement tools, don't worry. And then let's start with introduction and the preliminaries. Introduction. First, I want to start with the learning machine. What is learning machine? Learning machine is just actual machine learning. We can understand it as like that. We have some black box. We call it learning machine, and let's say it's F, and it takes some input X and transforms it to predicted output Y using the weights W. And this W is just tensor, or we can also call vector with some adjustable parameters. And consider it as a black box. We have the weights and we are just inputting X and we get the result Y. And the result Y is either +1 or -1. So it's just binary classification model. Let's give some examples to understand this learning machine. Let's take this example, f of X b is equal to sine of x times x minus b. Here, x times x is just basically dot product of x vector with itself, and x is just two-dimensional vector. So as you can see, if the vector components are x1 and x2, then x1 squared plus x2 squared minus b is the constrained function, and we are wondering about the sign of this function. And if it is less than 0, it means that there is a circle and we are looking into the inside of that circle, and if it's greater than 0, it means that we are looking at the outside of the circle. As you can see, these filled circles are denoting the plus ones, and the empty circles are denoting the negative ones, and then empty ones are inside of this circle, and plus ones are outside or on this circle. And another example of learning machine is this case. Let's say we have some weight and we are just multiplying x by w, and here w is just vector with two dimension again, and it is by the way, in the first example, this b is just scalar value because x dot product x is just some scalar value, and we are just subtracting b. And here, but the learnable parameters, we have two learnable parameters. The vector v, the w, it has two parameters, and when we multiply it with the x, which is also two-dimensional vector, but it's not the parameter, it's just the input, it can be anything. So we get something x1 times w1 plus x2 times w2. And if it's less than 0, we are classifying it as a negative one, and if it's greater than 0, we are classifying it as a positive labeling. As we can easily guess, it is just some basic line which is passing through the origin and dividing the plane into two parts. And then we can consider another learning machine. We can combine first two examples somehow. And here in this case, we have three learnable parameters, two in the vector w and one in the b. B is just scalar value. And this case is just differing from the example two by just adding this b term, and it gives some shifting to the line. As you can see, this one is not passing through the origin unless the b is equal to 0. So in this case, we have just some linear learning machine. I will give more intuition why we need to understand these learning machines. So now we have another preliminary that we should understand before going into the details of shattering and the VC dimension. It is that the general position. We will always assume that the points that we are given throughout this presentation are given in the general position. So we should understand what is general position. The general position in n-dimensional feature space is a set of m points where m should be greater than n, otherwise the statement will already be satisfied. So is in general position if and only if no subset of n plus 1 points of those m points lie on the n minus 1 dimensional hyperplane. By hyperplane, we just like assume that you can't find m plus 1 points that their span, as we know from linear algebra, their span is not making an n minus 1 dimensional hyperplane. In other words, they are not spanning some n minus 1 subdimensional plane. Let's give an example, you will understand it better. Let's say we are wondering about the two-dimensional feature space, and we have 5 points there, and the ordering is like this. We have 3 points collinear, like they are in the same line, and 2 points separated from those points. And in this case, they are not in general position because n is 2, and the general position requires that we don't have 3 points lie on the one-dimensional hyperplane, which means that we don't have 3 points they are lying on the single line. But in this case, we have 3 points, they are on the same line. In other words, they are collinear. So we can't consider this case as a general position. In general position, in two-dimensional case, we shouldn't have any 3 points they are making the line. And let's say in the case of n equals to 3, the three-dimensional space, we shouldn't have any 4 points that they are making the plane, and it's going so on. And I want to give several definitions. Like let's assume that we are given some learning machine f, as we said already. Learning machine f is just, we have machine, we input x, and it gives an output of y, and which is +1 or -1. And we have some learning machine f, we don't know what it is, but we have just learning machine. And we are also assuming that the training data is drawn from some IID distribution, which means that identically independent distributed probability distribution. Like assume that, like, it means that let's say we are classifying some image to the cat and dogs, and they are all coming from the same environment. For example, from we are just taking all the cats and dogs pictures from the same environment, and their distribution are the same. And some of them are taken from the home and some of them are taken from the forest. It's not like that. We are all taking them from the same distribution. It's basically saying that. And we are also assuming that the test data, the unseen data that we are more wondering about the accuracy here, is coming and will come from the same distribution, because the test data is always updated. So the current and the future test data set should be coming from the same distribution as well. The image or whatever the future space is, that it is coming from the same distribution as the training data. And the last assumption is all points are in general position. As we have discussed earlier, that they should be in the general positions. In other words, in two-dimensional, they shouldn't be collinear. In three-dimensional, they shouldn't make any plane. And then we can define some quantities like the test error and the train error. As we can see from their name, we have some learnable parameter alpha here, and this alpha is just basically the weights that we have already discussed at W in previous slides. And what we are doing is just we are taking the expectation of 1/2, which is just some normalizing constant, with absolute value of the grand truth labeling, like the correct labeling, +1 or -1, and the prediction of our learning machine. And we are taking all those differences, and then we are just absolutely summing them and finding the expectation of it. And in case of train error, it's exactly the same as the test error. There is just one difference. In this case, instead of looking at the test data set, we are just considering and we are traversing through the training examples. And here we are summing up from 1 to all the training examples, and we are summing up their the absolute value of their differences, and then we are normalizing by 1 over the number of training data there. And this ends should be R. I just forgot to change. And another definitions to understand, like let's dive into a bit more. Now, basically the VC dimension of above machine learning algorithm, let's say, is D. Like we have some algorithm here. We haven't talked about the VC dimension itself yet, but I'm just giving some motivation why we are using this. We have some learning machine F, and we are defining some D as a VC dimension of it, and we will see how we will define it, which is the measurement of the power of the F, like that learning machine. And if we have D, that the VC dimension, then we can the Vapnik Chervonenkis proved that the probability of test error is less than train error plus some constant, depending on the number of training examples, and this VC dimension constant and eta, which is the new constant, is this inequality will be satisfied with the probability of 1 minus eta, where eta is between 0 and 1. But in this case, we are assuming that D is way less than the R, because otherwise it may result in obvious overfitting, because we have more learnable parameters than we can assume it like this. We have more learnable parameters than the training examples, and obviously we will overfit. We can learn the training examples very well, but we will fail in the test error, so it won't be satisfied. But we are assuming that D is way lesser than R, and we can assume this. And this gives us a way to estimate the error on future data, because we don't know what will happen in the future. But actually, this gives us some intuition that if test data set is coming from the same distribution, then there is some, we can say something about the test error in the future, even though we haven't seen the data yet. And it will be based on only the training error and the VC dimension of F. Right, but there is just one problem: how we can define this D, like the VC dimension of D. This is the main question: how we can define and how we can measure the VC dimension. That's why we should understand the VC dimension. But before understanding the VC dimension, we should also go into the details of shattering. Shattering is also another important prerequisite to the VC dimension. And the shattering is basically we are again given some F. This is the learning machine again, and machine F can shatter a set of points x1 to xr if and only if there are possible, for every possible training set of the form x1, y1, x2, y2, xr, yr, there exists some values of those weights. We already discussed those w that gets zero training error, which means that like we can find there exists there exists a machine F. Like if we are given the machine F and we are given the set of x1 and x2 xr, and we are wondering whether this machine can get the zero training error in a way that we can tune this alpha, this weights in a way that we will get the zero training error. And if you are wondering about the total number of possibilities, basic counting implies that there are just 2 to the power of r such training sets to consider, because we have r set of points and y1 to yr, and all of them are getting either +1 or -1. And basic counting multiplication rule implies that 2 times 2 times r times, and then we will get 2 to the power of r. And if we are if we will consider the example when r is equal to 3, we can see there are just 8 possibilities. All of them are +1, one of them is -1, and 2 of them are +1, 2 of them are -1, and 1 of them are just positive, and all of them are negative. It's just for intuition how we are splitting the 3 points into different possibilities. Now I want to give some better examples on shattering that you can understand the shattering part. Let's say we are given this learning machine. We already discussed that this will give us some line, and we are just wondering, can this machine shatter 2 points which are in general position in 2D plane? Like we are given those 2 points. Can we find some W vector, like this 2-dimensional vector, that so that it will split those 2 points into the positive and negatives? Actually, the answer is yes, indeed we can. And the way that we are doing it is very simple. If we have 2 positive points, we just choose W as a 0 and 1, and the weights 0 and 1, and then the positive points will be stay on the positive side of the line, so it will be classified as +1 and +1. In the case of +1 here and -1 here, we will just draw the line like this, and in the case of -1 and +1, we are also drawing the same line, but the one thing that will be changed, the direction of the line. In this case, we are going into the up direction, and it makes this point as a positive, but in the second case, we are going to the below direction, so that this point will be classified as a positive one, and this point will be -1. And in the case of both of them are -1, we can just draw the same line as the positive one, but we will just change the direction, as you can see, 0 -1 instead of 0 1. Let's consider another example. In this example, as we have already discussed, again, we are given 2-dimensional input x, and we are multiplying, finding the dot product with itself, and then we are subtracting another constant or scalar value from that value, and then we get the sign of that expression, and we will get some f function, which is called learning machine. And we are wondering whether this can classify 2 points or not. But let's consider now this case. If we will pay more attention, and as we have already discussed, this is just basically some circle, and inside of this circle is classifying as negatives, and outside should be positives. It's very easy question, actually. Can we classify all the arrangements of these 2 points, +1, -1, +1, -1, ++, and -. Actually, it's impossible to classify 2 points in this case, as we can see, because the distance from the center, the origin, to the positive point can be less than the one with the negative sign. As you can see, if L2 is less than the L1, then the positive sign is less than the negative sign. And it doesn't depend on how we will draw the circle. The center is always in the origin. So if the negative point is inside of the circle, then the positive will be also in the inside of that circle. And if the positive is outside, then the negative should be outside. So 2 points are impossible in this kind of arrangement. That's why the 2 points are not possible to shatter in the case of circle. And that's all for shattering examples. And these are some examples. I took it from VC dimension of neural networks. There was a paper called like that, and it was very detailed and mathematical paper. You can take a look at that. And here U is the input space, which is in our case just two-dimensional case R2, and C is the training data that we are wondering about, the given example. In this case, we are given these two examples, and you can take a look at that, and you can see the results here, and you will try to shatter the 3 elements, and you can show why 4 elements cannot be shattered. But due to the time limitation and some low-level math things in this part, I will skip this part, and you can take a look at later. Now I want to introduce the VC dimension, which is the main content of this presentation. Now we are familiar with the general position. We know what's shattering, we know what's learning machine, and we have some assumptions that training data and test data are coming from the same distribution, which is IID, independently identical distributed. And we also familiar with the general position that all points are coming from the some generally position data, and we have some learning machine. We are all fine with those. Now we are going into the VC dimension part. Let's first define the VC dimension. As we have already talked, we have some constant D, which is called VC dimension, and which is very helpful to limit the test error, and we can take the control of increasing the model complexity or decreasing the model complexity by looking at just that probabilistic equation. The probability, as you can remember, probability of test error is less than train error plus some constant is 1 minus eta. That equation is very helpful. So we should understand what's VC dimension. And its definition is very basic. Again, we are given some machine F, which is just taking an input and making an output of binary classification +1 or -1. And the VC dimension D is the maximum number of points that can be arranged so that F can shatter them. But here, one thing you should understand is we are not considering all the possibilities of the points. If we can find just one possibility of the points, let's say in this case, we are just putting the points like 1 here and 1 here. And if we are just considering only those 2 points, that's enough. And if we can show that the F can shatter those 2 points, then we are done and we are fine. But we should consider all the arrangements of those points, like +1, +1, -1, -1, +1, -1, and -1, +1. I mean, if we claim that the VC dimension is at least 2, then we don't need to consider all the 2 points in the plane. We just need to find 2 points that are satisfying those conditions. But rather than that, we should consider all the possibilities of arrangements of negative and positives on all those arrangements, and this can be done in 2 to the power of r possibilities, as we have already discussed. Now let's take a look at this example. The VC dimension of this machine, which is f of x b, again sine x times x minus b, is d equals to 1, and we can prove it. And the proof is very basic. We already showed that it cannot shatter 2 points. As we have discussed, the positive point can be closer to the origin than the negative point. That's why we should consider we can say that d is less than 2, or d is less than or equal to 1. So in the case of 1, we have just 1 point, and we know that if it's negative point, the circle should strictly enclose this point inside of it, and we can achieve this by just drawing this circle with a radius of square root of b, which is greater than L. And we can learn another parameter b such that the square root of b is less than L in case of positive classification. This will give some intuition that in d equals to 1, we can find 1 point in a way that all the shattering or all the arrangements of it can be shattered. But in case of 2, we cannot find 2 points in a way that their all shatterings are satisfying all arrangements can be shattered by the given learning machine. Let's take a look at another example, and it's just basically the previous one, but I added another scalar constant here, the learnable parameter, adjustable weight here, a. Instead of taking just dot product and subtracting b, I'm also adding a term here, which is just scaling up or down the dot product of x. What's the difference between the previous example without the addition of learnable parameter a? Do you think like it will change the dimension of VC dimension? Because in this case, we didn't have a. Actually, it will change. And the reason is very basic, because in this case, we have dot product of x. And as we know that dot product is due to the Cauchy-Schwarz inequality as well. The dot product of x times x is just like, basically we are multiplying the same entries, the numbers twice, and we are getting square numbers, and then we are summing up them. So it's greater than 0. So this number will be always greater than 0. But while multiplying by a, we can adjust the sign of that number. As we can see here, 2 points are actually possible in this case, considering the flexibility of changing the sign, which alters the inside of circle to the positive labeling and outside to the negative labeling. As you can see from here, like we can take just a as a negative, and we can make it the inside of the circle as a positive and outside as a negative. But in case of previous example, it was like the inside was negative and the outside was positive necessarily, so we couldn't change anything. Here we have some flexibility, which allows us to classify 2 points. But how about 3 points? Can we do that? Because this finding is just implying that d is greater than or equal to 2, because we can classify 2 or more points, but we don't know, can we do that more part? Let's analyze that part. Actually, unfortunately, we can't do that. 3 points are impossible, and the reason is that they are in general position in the plane, so they have different distances from the origin. And let's say they have some arrangement, L1 is less than L3 and L3 is less than L2. And we should consider all the arrangements. In the case of the arrangement where the distance, the alternating points, I mean the +1, -1, and +1 are alternating starting from the origin according to their distance from the center, like this, then we cannot draw in a circle, because if we will draw the circle to keep one of those points, like then L1 should be strictly that point, and then L2 will be in the outside. I mean, L1 or L3 or L2 or L3. At the same time, 2 of them are in the outside or 2 of them are in the inside, but they should be classified as a different sides of the circle. It doesn't depend on the inside is positive or negative. So in this case, d is equal to 3 is impossible. We already proved, and we gave an example for 2 points. So it means that d is strictly 2. So the VC dimension of the circle, which is the flexible in terms of direction, as you can see from here, we add this a, then the VC dimension becomes 2. Let's take a look at another example, w times x plus b. In this case, we have some weight matrix, weight vector, and we are multiplying it by 2-dimensional input vector x, and we are adding some b term. Actually, this equation is very familiar to you, I'm sure, because if you worked on machine learning, you will remember that we are always applying this linearities in between the hidden layers, or the input layer and the hidden layers, different channels, but we are then applying some non-linearity activation functions. But before doing that, we are always doing this linearities, and these linearities are very important, and we are calling this w as a weight and b as a bias. And that's why this VC dimension is somehow related to the machine learning, and we will see how it's related and how it's applied. And in this case, we have just separating line. We already discussed that this will be implying that we have some line which can be any line in the plane, and which is just shifted from origin, or it's in the origin, it doesn't matter. So 1 point, one point is very obvious. If it's positive, we can make it in the positive side. If it's negative, we can make it in the negative side. And 2 points are also positive, because even we did this case without considering the b non-zero case. If we said just learn the parameter b as a 0, and we can just choose the w in an according way that it will classify it as a it will shatter it correctly, as we have already discussed this case in previous slides. Then the question arises that what about the 3 points? Can we do the 3 points? Can we shatter the 3 points by the separating lines? Actually, the answer is yes, of course we can, because they are in general position and no 3 of them are coinciding. So or collinear, that's the important part. So we can just assume 3 points in the general position, and we know that we can take any 3 points in the plane, and all we need to do is just considering all the alternating colorings, or in other words, the plus negative signs, like all the 8 possibilities, like all of them are positive 1, or 1 is negative and 2 positive, but they are all arrangements in the plane. As we can see, all the colorings or all the labelings can be shattered by the line, and we can also just summarize it as so any single of them can be separated from the rest of the 2 with the desired sign, along with the case 3 points are kept in the same side of the line with desired sign. It's exactly the same. If we have 2 points of the same sign, then we will just separate them, and if we have all the 3 points are the same sign, then we will just draw a line to separate 3 of the points from the rest of from just the plane. We don't have any other points. So the 3 is positive, 3 is possible, so it means that D is greater than or equal to 3. So what about the 4 points? Can we do the 4 points? And unfortunately, in this case, we can't do, and because 4 points, but in this case, we can't assume that the 3 points are, in this case, we just assume that 3 points are given in this case, in this, like this arrangement. But in the 4 case, we can't assume that they are in some shape. We just know that they are in the general position. And in general position, there are 2 possibilities of 4 points arrangement. Either they are making some convex diagram, convex quadrilateral, or they are making some triangle. Inside of triangle, there is a point. And in both of the cases, there is an arrangement, the arrangement of positives and negatives, in which the model fails to shatter. As you can see, in this case, no matter which line we will draw, it will always keep this 2 different classes in the same side. And in this case as well, we can separate 3 plus ones from the negative 1, which is inside of that triangle, strictly inside of that triangle. You may also ask why we are not considering the case that this is on the line of this positive line, positive points. We can't consider that case because we are assuming that the points are always in the general position. So they're in the plane, there are no 3 points that are collinear or they are in the same line. So we are done with the separating line case as well. Now let's move on to another separating line, maybe separating hyperplane. We can also say half space, and we can also call it visa dimension of linear classifier in m dimensions. It's exactly the same as the previous settings, but in this case, we had the input as a 2-dimensional. In this case, we have it is dimension as a m. It's a bit harder case, but in real machine learning, we are using this case because we have some input feature space, and we always change the dimensions. So the feature spaces are always changing the dimension. So it's better to deal with the different, the flexible, the dimensions. So in this case, what do you think? What will be the resulting visa dimension? D. We should find the D, 1 or 2 or something related to m, because in this case, as you can see, it is just basically m equals to 2 case, and we found it's 3. So it's more reasonable to questioning that can the answer be constant or it's related to the m? Actually, the answer is related to m. Let's first prove that D is at least m plus 1. If we want to prove that D is at least m plus 1, it means that we should find some m plus 1 points in the plane, in m-dimensional space, in which we can arrange those, in any arrangement of the positive ones and negative ones, there is a shattering of those points into there is a linear classifier. There is a shattering that separates those positive ones and negative ones in a way that positives are in the positive side of the hyperplane or half space, and the negative ones are in the negative side of it. And it is possible to do that. Let's just consider the x vectors, the input vectors, as identity, the standard vectors as we know from linear algebra, like 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 0, 1. Basically, we are taking the i's input as a vector whose i's entry is 1, and the rest of the entries are 0. And then we are making another matrix, which is called this large X, and we are adding all ones in front of it. So this matrix is m+1 times m+1 dimensional vector, and we are adding some random zeros here, lots of zeros here. Explicitly it's m times zeros. And we are making some large X matrix here. And another way, and also we have this the W weight matrix. It is basically some m-dimensional vector, but in order to avoid dealing with all input vectors separately, I'm just concatenating the same weight matrix m times with each other. But the thing is, in order to deal with, we should also consider the bias term, this B term, and that's why I am considering this B inside of this W. So I will have another learnable parameters of m+1 times m+1 dimensional. And I'm basically just concatenating them. And now I have some linear algebra task. I have two matrices and I am multiplying them and I will get some result. I'm wondering whether I can do that or not, whether I can find m+1 parameters, which are B and M parameters of this W, that they will result in, when I will multiply it by this, then they will result in some Y. The Y is some any arbitrary arrangement of plus ones and the negative ones. Actually, it's possible. And the reason is basically, what's the original equation? Some the concatenation of W and the B times X is equal to Y. And in any arrangement of the Y, we know that this matrix is invertible because we can easily find the determinant that it's non-zero. So if it's non-zero, then it's invertible. If it has inverse, then I will just multiply both sides by inverse of X, and I will get the concatenation of W times W and B is equal to inverse of X times Y vector. And Y can be arbitrary arrangement of plus ones and minus one. There are 2 to the power of m+1 possibilities in this case. And then I will get m+1 parameters, and they will be uniquely defined, and they will by this I can find what are the weights and what are the bias here, and basically I can find m+1 points in m-dimensional space, which gives the result for the this learning machine, linear classified in m dimension. So it implies that D is at least m+1, which is a good result. But we are also wondering about the upper bound because it doesn't guarantee that the result is m+1. In this case, we should prove that in any arrangement of the points, not the plus ones and minus one, any arrangements of the points itself in m-dimensional space, there are no m+2 points that can be shattered. So, and this can be done by proving it by considering their linearly dependency and affinely dependency, because m+2 points in m-dimensional space are affinely dependent, but it requires some more mathematical background. So I will skip this part, and we can assume that it can be done in an easy way, and we can assume that D, the VC dimension, is less than m+2. So we already proved that D is greater than or equal to m+1, and we know that the VC dimension is some integer number. So we can basically find that D is equal to m+1. So that completes the explanation of the VC dimension part. I know this last example was requiring too much mathematical background, but it was the most interesting, I think, example, since it's the main way that we are applying this VC dimension to the machine learning. Now, I want to move on to the last part, applications and the beyond. And in the applications part, how we can apply it. Like, as we have already discussed at the first stage, we know that it gives some intuition and it gives some constraint or limitation on test error, that we have some only the train error, we have some limited number of points, we don't know what will happen in the future data set, we just know that they are coming from the same distribution. We want to balance them, we want to find what's the upper bound of the test error with some fixed probability, and we can do that by VC dimension, and which helps us to find which model complexity is good to achieve the best performance and without doing underfitting and overfitting. As we know, like underfitting and overfitting are two dilemma, like they are very opposite to each other. So at some point, if it's overfitting, then there is no underfitting, and if there is underfitting, then there is no overfitting, and they are not correlated to each other. So we want to find a point that is the best point for preventing the underfitting and the overfitting. And this VC dimension is helping us to find that. And let's say those S1, S2, and SK, they are different models with different complexities, but the same VC dimension, and they have different curves. And this VC dimension is helping us to find this dotted line, which is the ideal balance between bias and variance. And in other words, underfitting and overfitting. And goal should be to choose a model with a complexity that's just enough for a classification task. Any less than this may result in underfitting, that we will get very bad training and test results, and anything beyond will give us some overfitting, which means that we can learn the training data set very well, but we can't perform well on the test data set. And so basically in machine learning, this VC dimension is helping us to determine the best way, best balance between underfitting and overfitting. Then another, like in different aspects of the science, we can use this VC dimensionality in decision trees, because we know that those decision trees are very like too much. They are very. They are very. They can be overfitting very well, so we should consider their case as well, because we are always splitting the nodes, and if we have more nodes than the training example, they will be probably overfitting, so we should consider this case as well. And there is VC dimensionality of perceptrons, which is also preventing their overfitting and underfitting, and it's finding the best balance between underfitting and overfitting. And there are different ones as well, and the main one is the current usage is the neural networks and SVM as well, support vector machines. And the main goals in those above mentioned aspects are the understanding which learning machines are more and or less powerful under which circumstances. And also we should use as a goal, we should use the structural risk minimization for the choosing the best learning machine among all of them by finding the VC dimensionalities. And at the last, I want to ask a question, like which model selection method is best, do you think? Like, because we have another way, like cross-validation, we can cross-validate the models and we can choose the best. We have another AIC or Bayesian information criterion, BIC, and this last one, VC dimensionality. And it depends on, highly depends on the situation. And in case that like we are only wondering about the training error, then we don't need to use the cross validation. The rest of them are fine. But because the cross validation might have more variance. But in the case of we are wondering about the test dataset, it is more reasonable to use as well the cross validation as well. And you can read the rest of the test cases and use cases scenarios here. For example, the most important one is also Bayesian information criterion, because it's used if we want the best structure instead of the best predictor. For example, class string or Bayesian networks structure finding algorithms, we are mainly using the Bayesian information criterion instead of the cross-validation or VC dimensionality. But in the case we want the best predictor, without considering the training error, cross-validation is also good. In case we are just wondering about, we only need the training error, then VC dimensionality is, I think, the best, can be considered as the best. But there are many alternatives to those, and it's highly depending on you and your model and your task as well. So it's just end of my presentation, and I just want to give you some takeaways you can take from this presentation. I know it includes lots of math, and I'm sorry if I couldn't explain well some mathematical terms and parts. But after this presentation, I think you should be able to understand the learning machine, the black box in machine learning that we are always using. It takes input and gives some output. Then shattering, which is the mathematical term, just classifying positive and negative points, or just separating two different points from each other, which is just binary classification can be. And then VC dimension, which is the greatest number of shatterings in some fixed dimensions and in fixed settings of the points, and with different all arbitrary +1 and -1 arrangements. And you should also understand what are the applications of VC dimension in neural nets and decision trees and in other aspects of the science in machine learning. And you should also understand the various methods to measure the power of a model other than the VC dimension, like cross-validation or Bayesian criterion and others. And this is the end of my presentation. Thank you for listening.
Thank you. Thank you very much. So, as usual, let's now take a short break, 3 to 5 minutes, to digest and to come up with comments, questions, and about the content. Not about the quality for now, about the content. Okay, so I'm going to stop recording now. Okay, thank you very much again and welcome back after the break. So, yes, you recall the presentation about perceptron theory, right? And one important part of the perceptron theory was that in order to classify points on a plane or in a hyperspace using a perceptron, that's equivalent to saying that this class of points can be separated by some line or some hyperplane, right? Points that are considered positive from the classifier must lie all on one side of the plane or line, and all points which are considered negative with respect to the classifier must be on the other side. So that's about linear separability. And if you have a set of points, and if you can thus separate it, then it can be learned by perceptron. And the generalization we consider here is that now it's not necessarily linear separability, but for example, separating by disks or by circles, so that all positive points must be inside the circle and all negative points must be outside of the circle, or vice versa. And more generally, ranges, that's the technical term, which ranges are necessary in order to be able to classify point sets, all point sets of a certain size. That's the VC dimension. So that's a very important concept on the intersection between combinatorics and geometry. And Abbas, thank you so much for presenting that on such short notice. Yes, Abbas only learned that his presentation is due already today. He learned that I told him that only 2 days ago. And so that was a lot of work for him on short notice. Thank you so much. So yes, with that being said, now about questions and comments from you about the content of the presentation. Yes. Yeah, so the ordinary one-layer perceptron, that was about linear separability, but then there are multi-layers, right? That's one way of generalizing the perceptron. And this is another direction of generalizing, by generalizing from linear separability to other, separating by other geometric objects such as circles or triangles, or in higher dimensions, simplices. And all these give rise to so-called range spaces, and every range space has such a VC dimension. And yeah, as we're going to see in the next talk on next Tuesday, this VC dimension is closely related to complexity, but that's a topic for next week. So for now, please ask questions about the VC dimension, or give comments about the VC dimension and about shattering. These are the two concepts that you should take away from today, because that's what the next talk will briefly recall and then build on. So hands up, who has understood what it means to shatter a point set? Of course, that's a subtle concept. It refers to subsets of the point set. So shattering a point set means that every subset should be separable by the type of ranges, by either by a line or by a circle or by triangle or in higher dimension. That's what it means to shatter a point set, that every subset should be separable. And the VC dimension is the largest number of points that can be shattered. So there's a, yes, thank you for recalling that slide. And there's a subtlety here. You write the large maximum number of points that can be arranged. So yeah, so right. Could you recall what it means for the points to be arranged?
Yeah,
So,
like in terms of arranging, I mean like we are not considering all the positionings of the points in m-dimensional space. We are just considering like if we are claiming the VC dimension is D for some machine F, then we need to find some arrangement of the points on that m-dimensional space in which all the arrangements of plus ones and minus ones can be shattered. Like we are not considering all positionings and all arrangements of plus minus ones. We are considering like we should find just one positionings, and according to that positioning, we should be able to shatter all arrangements of plus minus ones on that positioning. So that can be arranged, not the must be arranged and must arrange all those possibilities. That's why I was in this case, like in the case of linear class Y, I just took basically some identity matrix and I just took standard vectors and I didn't consider all the possibilities here.
okay, so let me ask the opposite direction, who did not understand what it means to shatter a set of points. If you did not understand that, then please raise your hand now. Okay, good. Everybody understood. And then based on that, the VC dimension being the largest number. And could you recall the slide with the examples of VC dimension of various spaces?
For example, in this one, we are considering the circle in which we are also adjusting the coefficients of x squared and y squared. And in this case, like in the case we are not putting this A, we are only we have only the inside as a negatives and outside as a positives. But in this case, we have inside we can make inside positive and outside negative because we have some flexibility with this A constant.
Right. And you had a slide with examples of other spaces listing theirs, right?
This one?
There was a slide with a list of various VC dimensions. Yes, this one.
Okay.
Right.
Yeah.
Thank you. Excellent. So the first one is where the ranges are open intervals in one dimension. These are the ranges. This is kind of a special case of linear separability, linear, because in one dimension, a linear subspace is simply a point, right? Then item 3 is about two-dimensional half spaces. Item 4 is about two-dimension all convex sets. This is a more general class of ranges, and they can, of course, separate more types of point sets than just half spaces, right? Because every half space is a convex set, but convex sets are more powerful. So if you can learn half spaces, then you can also learn convex sets. And if you only can learn convex sets, then that means not necessarily that half spaces are sufficient. And this is reflected on the bottom of the slide, where, yeah, various VC dimensions are mentioned for these kind of ranges. Yes, I understand that when first being presented with such a concept, highly mathematical, it can be overwhelming. So yeah, how about we close the discussion about the content, and yes, next week's presentation will kind of maybe recall these concepts and then proceed from there. So now we'll move to the part where we evaluate the style of the presentation, provide feedback to the style of the presentation. That's where I turn off the recording. So yes, thank you very much for attending. And 1 second. Yes, then class is dismissed, except for Sarah. Sarah, could you stay online so that we can discuss your upcoming presentation? Everybody else, thank you very much, and goodbye. Have a great evening.